So today we have a smallish to medium-sized diamond from Brazil. These are being sold on the internet as amethyst, Chevron amethyst, and you can see the chevrons there. But it is not quartz at all. And it is quite beautiful, as you can see. It is a carbon crystal. The diamond allotrope of carbon. First of all, quartz does not have planes of cleavage. Can't. It's not made the same way. Quartz is 7 on the Mohs scale of hardness. Ruby, I have a small one here, you can see, that is perfect to find out if this is softer than ruby, which is 9 on the Mohs scale of hardness. This will not scratch it. It will just slide off of it like an ice skater. And so what I'm going to do is take that and go across my beautiful ruby. Didn't hurt that much. And you can see the scratch there. Right there. Let's see if we can find a clean surface. Here we go. We'll do this. See, there's some sort of greasy stuff on, probably hemp seed oil from all of my diamond lapidary stuff. Let's see here. Let's see if I can find a sharp point. Hold, please. And there's my scratch right across there. You see it? Now I'm going to try to wipe it out with the finger here on one end of it. Okay? So we can sort of trace that. Let's see. And there is actually a scratch in the ruby underneath it there. You can see it. And there there's the scratches right across there. Whoops, right where that light just is. You can see it, thing across. Yeah. Cool. You know what? Ruby is 9 on the Mohs scale of hardness. Quartz can't even come close to scratching it. Not even close. It's 2 orders of magnitude harder. That's 100 times harder than quartz. Ruby is the 2nd hardest mineral in the world, and probably in any world, because we all have the same 92 elements. This is aluminum oxide. It is 9 on the Mohs scale of hardness. This is a 10 on the Mohs scale of hardness. It is either a diamond or naturally occurring carborundum called moissanite in its man-made form, but we call it carborundum. And this is not. This is a diamond. This is a diamond. And it's a beauty. It is truly, truly spectacular. Does not need any help from me. The hardness test is absolutely it takes the guesswork out of mineral identification. When you know how hard a rock is, they have a very specific order of getting harder and harder up through quartz and into corundum and then diamond. But diamond is not just an order of magnitude harder than corundum. It's 5 orders of magnitude harder. It is 100,000 times harder than quartz. Or than aluminum oxide, which is 100 times harder than quartz. So this is 100 times 1,000, 100,000 times harder than quartz. Wow, huh? See, science is not a bunch of blah, blah, blah and theories. Science is about measuring the universe we live in. And we compare those measurements. We do them not once, not twice, but hundreds of times, man, sometimes thousands of times. I have done hardness tests on this particular rock at least 100 times, at least. It's not that I think I might be wrong. It's that I absolutely know I am right, and I show other people. Diamonds form planes of cleavage that you can see here, these striations in the crystal structure are little rows and columns of carbon atoms, carbon atoms are all the same size. So they all line up in perfect little rows and columns. And that's what you're seeing here. That's what those lines are, those striations. As the crystal grew, it grew along those planes, one at a time. But it makes diamonds so very, very clear. We can see all the way through to the other side of this diamond. Look at that. Isn't that? The long way. You couldn't do that with quartz if it was a tenth of that size. Quartz doesn't let you see through it like this amethyst doesn't. It's not clear like this because of the double covalent bond between carbon atoms in a diamond. They have 4 electrons in their outer valence orbit, and they share those 4 electrons with each other because the tremendous pressure underground and inside a fault line squeezed those atoms of carbon so closely together they can share those 4 outer electrons with each other to become the stable octet that all compounds and elements require to be stable in our universe. Carbon is a semi-metal. It has 4 electrons in its outer valence orbit. When they're squeezed so tightly together that they can share them, they become clear. Now, carbon, generally speaking, let me see, I've got one right over there. Where'd they go? Whoop, 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 whoop. There we go. See that black thing there? That's carbon. That's the other allotrope of carbon. Called graphite, huh? That's what graphite is. Same as inside of a pencil. They come off in layers. And there's why. There's the layers. You see the layers. And a pencil like writes because it's leaving little particles of layers like this of carbon. And they all fit together very nicely because they're all the same size. And that's why you get these planes of cleavage. Now, silicon dioxide does not have the same size elements inside of it. It has silicon and it has oxygen. And so it's the silicon tetrahedron that creates the symmetries in a quartz crystal. They are bound, the oxygens to the silicon are bound together at 144 degrees. And all of the angles in a quartz crystal are multiples of 144 degrees. That's the difference between carbon and silicon dioxide.